One of the most important ideas in calculus is that of the derivative. So let's dive right in with the definition and then we'll expand it from there. The derivative of f is the function f prime of x equals the limit as h goes to 0 of f of x plus h minus f of x all divided by h. So note that this apostrophe looking thing right here we pronounce as prime. So we say f prime of x prime. Okay, let's get a couple more definitions just so we have a working vocabulary. Let's see, so if f prime exists, we say that f is differentiable at x. And furthermore, if f is differentiable at every point in some open interval I, we say that it's differentiable on I. Okay, so that gives us a little bit of language to work with. This definition of a derivative does not come out of thin air, and it means something. So let's just take some arbitrary function f here. Okay, so here it is. And we want to know the slope here at a single point. Okay, so slope here. Okay, so everything we know about slope, though, up till now, we need 2 points for a slope. This is called the secant line. So let's draw the slope between 2 points, like so. Okay, we want to know the slope at point x here. Okay, so we'll call that x. That's what the derivative tells us. How does it do it? Well, you take a second point, and let's call this distance here h. So then this point up here must be x plus h. And then we just take the standard definition of slope of that blue line there, that secant line. It's rise over run, so let's see what the y values are. So right here, the y value is f of x. Right, if we were to go over onto the x-axis, or over onto the y-axis, and over here we're at f of x plus h. So let's just do rise over run. We'll do the y's over the x's. So the slope here would be, let's see, so let's do f of x plus h minus f of x, so that's y2 minus y1 over x2 minus x1, x plus h minus x. Okay, we can clean that up a little bit to give us a slope with the secant line, f of x plus h minus f of x all over h. But we want the slope at a single point, not that line that goes through 2 points. So we'll do a little trick here and we'll just let that h shrink to 0. So when we let this h shrink to 0, we're just pulling this x plus h in toward the point x. Right, so this is just coming in towards x. And you get closer and closer and closer until you're just on top of x itself. That'll give us the slope at the point x, which is what we want to know. How do we represent that mathematically? Well, we have a tool for that. It's the limit as h goes to 0 of all of that. F of x plus h minus f of x all over h, and voila, we have the definition of a derivative. Now there's lots of different notation for representing the derivative. So let's just take a look at some of that notation. Okay, well, we already have seen f prime of x. Another common way of talking about the derivatives is to say something like dy dx. That's the derivative of y with respect to x. Right, that's pretty common. Sometimes you see it as this big D sub x of f of x. Every once in a while, that's not quite as common, certainly maybe in some other fields besides calculus. Maybe y prime, you see it like that, just y prime, because we're using f of x and y interchangeably here. Sometimes in physics you see it as y dot, that's specifically the time derivative, right? And oftentimes, right, anytime we're applying this to nature, at least a lot of the time, certainly not any time, but a lot of the time, you're doing it with respect to t. So it might be something like ds dt, derivative of position with respect to time. That gives us velocity, right? Something like that. if you want to evaluate the derivative at a specific point, a, so let's do that at x equals a, right? Sometimes you want to know the derivative not of the entire function, but you want to say at a specific point. You could say something like this. You could write it as f prime of a, or maybe dy dx evaluated at x equals a. Right? You draw this line here, this big vertical line, to say I'm evaluating it here. Oftentimes we also do like df dx, right? df, right? Maybe something like this at x equals a. So that's one I didn't list up here. Sometimes you say d by dx of f of x, right? I'm taking the derivative of f of x. That's another way of writing it. These are all equivalent. We also might just say y prime at a, something like that. Okay, so there are several ways to talk about the derivative. Let's try to compute a derivative with an example. Here we have f of x equals x squared plus 3x, and we're asked to find f prime of x, the derivative, and f prime of negative 1, which is the derivative evaluated at negative 1. Okay, so let's bring up that limit definition of the derivative, which I highly recommend setting to memory. This is one of those things in calculus you should just have on kind of instant recall there. So here we have f prime of x equals the limit as h goes to 0, f of x plus h minus f of x all over h. It just rolls right off the tongue. And let's just dive right in here. So we have the limit. Let's back up and say the derivative as a function, okay, is this limit. And it just comes down to a lot of algebra from here. Algebra is always the hardest part of calculus. Okay, so now I want to plug in all of x plus h. Every time I see an x, I'm going to replace that with parentheses x plus h. So instead of x squared, it's parentheses x plus h squared. Instead of 3x, it's plus 3 parentheses x plus h. Okay, so there's my f of x plus h bit. F of x plus h. Then I subtract off the original function, so minus, and it helps to think of this as having parentheses around it, right? Because you want to subtract off the entire function. So I'm going to add these parentheses, and then you just essentially cut and paste this function right back, right? Because there's the function that is f of x. So here we just write x squared plus 3x, okay, all over h. So this is that difference quotient you may have practiced many times in past courses, in this course. Okay, so let's see here. So this bit here is f of x. So we have f of x plus h minus f of x all over h. So 90% of this is just setting it up correctly like that. All right. The biggest mistake here is to do something, so what I'm about to do is wrong, is instead of doing f of x plus h, people just have a tendency to do f of x plus h. And so they'd say x squared plus h plus 3x plus h. Something like that. Don't do it. Right? You want to make sure that that entire x plus h ends up inside the parentheses. Okay, so when we do this, we're letting h go to 0. So our goal is going to be to get this to cancel out, because we don't want to be dividing by 0. So there's our goal. That's just something you can kind of keep your eye on as you work these kinds of examples. All right, so let's see what we can do here. Let's see if we can make that h in the denominator cancel out. So we have the limit as h goes to 0. Let's expand this. We have x squared plus 2xh plus h squared plus 3x plus 3h minus x squared minus 3x. We are knee-deep in algebra here over h. Well, you should get some nice cancellation here. That's the whole idea. So our x squareds go, 3x's go. So I'm liking where this is going. Okay, so we now have the limit as h goes to 0. You do need to write limit again each time, because this is a limit that we're taking here. So we have, what's left here, 2xh plus h squared plus 3h all over h. Well, we can factor an h out of the numerator there. So we have the limit as h goes to 0. Let's pull out an h there. You could also just cancel it straight up, but I'll factor it out. That leaves us with 2x plus h plus 3 all over h, and finally our h's cancel. That's what we wanted to have happen. So this is the limit as h goes to 0 of 2x plus h plus 3. And finally, we can just take that limit, let h go to 0, which leaves us with 2x plus 3 for our final answer. That is indeed the derivative. So let's be clear, this is f prime of x. Okay, now to evaluate this derivative at the point -1, at x equals -1, we simply plug it in. So f prime of -1 is then, okay, well, 2 times -1 plus 3. Okay, so that equals 1. Nothing too fancy there. This is tedious. The good news is we'll get rules for differentiation that will allow you to evaluate something like this derivative here. Let's go back up. This derivative, there's the original derivative. You know, after a few sections, you'll be able to evaluate this derivative, I would say, in half a second. And I'm not exaggerating. You won't go through this entire process, but we'll learn some shortcuts that will take it right down to the derivative very quickly. So don't despair. But first we have to do the limit definition. Then once we deeply understand what the derivative is and how it works, we can get all the shortcuts.